ไลฟ์ on YouTube แล้วด้วยนะ Okay, Sunny. Good afternoon, everyone. Today we have an individual seminar, Big Point Lab. We have three presenters. The first is Mr. Sunny, the second is Adamo, and the last one is Mr. Arif. Okay, Sunny, if you're ready, you can start.
Okay, thank you very much, Mimi. Thanks everyone for connection and for the opportunity to present my work here. Today, I would like to discuss on solutions of monotone variational inequalities, and it has to be Golden ratio algorithms, and within the framework of geodesic spaces on some special spaces. Actually, we start with the general motivation of variational inequality. First of all, consider a smooth function, let's say f, and once you have f, you can see that if f is convex and smooth, then this condition is guaranteed. In fact, this condition characterizes the convexity of f. So based on this property, one can guarantee that U is a minimizer of f if and only if this inequality holds. Of course, when seeing this, then you can, a natural question is that what happens when you have an operator A acting on U, then we have this W minus U resulting on inner product by greater or equals to 0. This is, of course, important property that comprises minimizers, saddle point, and maximizers of certain objective functions. So in the convex analysis, actually the maximizers are not important for us. Why is it so? Is because whenever you have a situation requesting maximizers, then one can use minus of F to get it from the minimizers. That is important property. So the major things, that's why you can see this one appears to be shared. But so the major concern is minimizers and saddle points here. And this is it as it is defined. This is variational inequality in the classical sense. That is in linear setting, or let's say in inner product space. Okay, it has application in machine learning, robotic motion control, and several other natural arising situations. Of course, you can have the application of that. So there are several algorithms in the literature regarding variational inequality. The most prominent one, starting from projected gradient method, which is nothing but Pickard iteration. Actually, this is how it is defined. And then you can see this is Pickard iteration with the operator T being the one stated in blue here. And this guarantees that the sequence here converges to a solution of the variational inequality. But what kind of convergence here? Is because it's Pickard iteration, definitely this gives what they call strong convergence whenever A is alpha strongly, if A is strongly monotone. So, but when you change A to inverse strongly monotone, then this operator T will result to Krasnodębski iteration, and then we have Krasnodębski iteration. This one will give you nothing but a weak convergence. So you can see changing the operator affects the convergence result of the algorithm. So what happens when A is simply monotone? If it is monotone, of course, as Kofolovich observed, that this may not even converge. So as a result, Kofolovich now extrapolates this projected gradient to come up with what they call extra gradient approach. And this extra gradient approach successively approximates solution of variational inequality in the case where the operator is monotone. So this is very interesting result. However, it has its own drawback. One of the drawbacks here is that it comprises of two projections. At each iteration K, one need to compute projection 2 times. So what is the difficulties or what is the problem associated with computation of projection? Remember, projection is a minimization problem. Therefore, it's computationally expensive even for the computer to carry on unless if you have explicit relation. So extract gradient now added a burden to the iterative techniques, even though it takes care of the case when A is monotone, but this is a serious problem. We're having two projections. So how do we reduce that? One way to reduce that is the method of subgradient extract gradient. This subgradient, you can see this projection is replaced by half space. And this is how it is done. Generally, the iterate for extract gradient, we take a point here, you now get this translation. From that to one, then you have to project back to the set, and it continues this way until you reach to the desired element. So, but for this one now, this is how it is updated. Some of the updated element for the SK plus one will turn out only to be on the hyperplane, on the half spaces. Actually, then that simplifies the situation because projection on half spaces here is explicitly defined in the literature. You can find several books that state the explicit form. So this is like only computation of one projection at each iteration. This is significant improvement. So look at the chain actually. The first one here is around 1964, reaching, but a couple of it is around 1976. And then this one is nothing but 2011. This is very recent result by Senso. And so in that direction, several authors also discovered their own approach. One of the major or prominent methods known nowadays is projection contraction method. And of course, this is how it is done. And it's also work for monotone. This is very important. And it's only required one projection per iteration. This is another approach as it is. Another method is Eng method, which also requires only one projection, which is very successful. And another method is Golden ratio techniques. So for this Golden ratio, you can see that when Milisky here provide the Golden ratio around 2020, then this Golden ratio is even successful in approximating more general problem, not just a single variational inequality, but also a mixed variational inequality, and also where the operator T may not necessarily be monotone. So this becomes very successful, and it only requires one computation of projection. This is proximal, of course, for the generalized problem. However, you can once you are dealing with the projection, then it turns out to be just the projection. In the case where G is nothing but the indicator function for on C. So that one turns out to be the projection. And this is very successful method, and it's only discovered when 2020. This is very recent, then several modifications can be found, but these are basically most interesting methods that one can see in the literature with their motivation being clearly attached with manuscripts. So now the question is, what happens when you are not only in linear spaces? For example, now, let's say we have a metric space HD, and then this metric space is such a way that for every 2 points you have, there exists a map satisfying this property. Such kind of mapping is called geodesic path. And then the segment of the mapping is nothing but the image of the map, which is called geodesic segment connecting the 2 points. And then when it turns out for every 2 points in the space, this kind of property is satisfied. This space is called geodesic space. And if it is unique, for every 2 points, the connectivity is uniquely defined, then that is called unique geodesic space. And that case, an important example of such situation is KMUTT spaces for every K in R. So these KMUTT spaces are Alexandrov spaces that are bounded above, of course, and this has been studied long ago, but nowadays their own applicability have been traced out, and a lot of things are now discovering. So the KMUTT is coined by this mathematician Gromov, and is after the name of Katan, Alexandrov, and Toponov in the recognition of their work. And then for case when 1C Hadamard space is after Solomon Hadamard. Of course, these are French and Russian mathematicians. Okay. An important part of this space is its cut zero space. One interesting property of cut zero space is that it has certain structure that mimic the situation of flatness. For example, it's resembled the Euclidean space, even though it is not, but that gives it a unique property. Example of such include pre-Hilbert spaces, Hadamard manifold, R3's Hilbert ball, all cut K spaces that are for K less than or equals to 0. So all of them are cut zero spaces. Of course, you can see now, if you try to see the intersection between cut zero spaces and norm space, is nothing but pre-Hilbert space. And this is generally metric space. All geodesic spaces based on our definition are metric spaces, of course. You can see how it is. So this is metric space with special structure. So, but of course, in that space, we lack several things like subtraction, multiplication, non-inner product, and so on and so forth. But yes, nevertheless, we still have complexity in some sense, defined this way, for example. And then this is T-convexity property. That is to say, the distance function is convex. In that sense, one may recall Takahashi convexity. That's why I just call this T-convexity, of course. And we have seen inequality, which of course is motivated by Upler's identity, which is very prominent in the case of Hilbert space. And but here we have inequality instead of just equality. This is important, and based on this, one can even see that every Hilbert space is a cut zero space. So yeah, a lot of properties are there. For example, closed convex set are uniquely proximal. Projections onto closed convex set are non-expansive, and so on and so forth. A lot you can have. Of course, just try to visualize the structure or the geometry of this setting. When you equip R2 with the usual metric, then it turns out that triangle is nothing but this one, just straight line connectivity between the 3 points. However, if you equip R2 with radial metric, then triangle is nothing but this one. So this give you, if you equip with ribbon metric, we have triangle this way. Of course, one will see that, of course, this kind of situation is very flexible because you can always change the distance and then you have a different structure. So the interesting part is that all R2 with all these distances, once you equip R2 with any of these distance, then you have a cut zero space. In fact, a Hadamard space. And that's very, very, very important. And one may think of connectivity around, physical phenomena where you can think of having a crowded area, and you want to have, let's say, the optimal location where everyone from the crowded places can access easily. And in that case you want to build an emergency medical center, for example, then in that case, one needs to employ this kind of distance, radial distance, especially when the connectivity is orthogonally stretched away from the major road. And when we have some situation like that, which is not directly, for example, there is no connectivity here, then using the Euclidean setting will not be the optimal result. So the befitting distance to make use is this one, and then using that you can optimize just by getting the minimizer. Of course, additional thing you may recall that this space, of course, does allow non-convex set to be appears as convex. For example, this is non-convex, this is non-convex. But once you change the metric, for example, this to radial, it turns out to be convex, and this one also turns out to be convex. So these are interesting. Another thing is non-convex function can be convex. So in that way, we have additional property. So the major question now is, what is variational inequality in this setting? So because we are dealing with Golden ratio, and of course, like I mentioned from the first paper of Golden ratio by Bliski, it's also applicable to generalized variational. So here now, this is it. If you have Q here, where this Q is nothing but the quasi-linearization taking 4 different displacements. And if it turns out to be bigger or equal to 0, it's that is just a variation inequality. But when it is added with certain proper and convex lower semi-continuous function, then it becomes rational, and this is generalized problem. Of course, when phi here is the indicator function, then this turns out to be the classical variation inequality, especially, and when you turns out, when you replace, when the setting is considered to be Hilbert space, then this reduces to the classical variation inequality, which we stated earlier. So our interest here is to solve this particular problem based on this. The first condition is that the solution set is not empty. The second condition is that phi is proper lower semi-continuous function. And then this is monotone type. By monotone type is simply monotone, because this reduces to the monotone whenever you are in classical sense, because you can change this and then you see I minus t is monotone is the same as this. So in this regard here, based on this, we call this monotone type. Remember here, we say G has to be from the domain of. Why is it? Because G, this is not G, but by phi here, as it is. This is just a typo. This is supposed to be by phi. So when you have this, remember it can take up to infinity. So when we are restricted to this one and this inequality is satisfied, then it's okay. We don't need to care much about the case when it is infinity. So this is the case when it is, and this reduces. This is what we have, and this is the problem studied by Milisky. Of course, for our own situation, we require certain conditions. The first condition is that we require a map to be T transport. We define this T to be T transport if this condition is satisfied. Of course, this is interesting. And we give an example in the case of Hilbert space. You can take this example. Then this turns out to be T transport. Yes. And once you put this one, and the algorithm we consider is this one. As it is here, you can see this is well defined because this phi, this phi is bigger than 1, of course, and if it is bigger than 1, and 1 over 8 will turn out to be within 0 and 1, and then we have this is well defined based on the criteria mentioned earlier, and this is also well defined because lambda k is coming from here. So once we have this algorithm is well defined in the situation because the proximal also is clearly well defined. So we have, in the case we have at zeros, firstly satisfying L Lipschitz condition, that is to say it's Lipschitz with constant L, and then satisfy the C1 to C3 as mentioned in the sense the C1 C3 is being monotone type, and also the solution set is not empty, and then and that is proper lower semi-continuous. So in that case, if lambda k is a sequence that converges to some element inside this interval, then UN generated by phi delta conversion. Actually, this is convergence is not just for the UN, but rather for the two sequence here. I mean, this is xk and yk. So for the two sk and yk, all of them converges unanimously. So in that case, we give an example. You can take R2 for example, and if you take R2, we define distance this way, and if we define distance with this, turns out to be geodesics, and then you define T here, T is monotone type, satisfying all the condition there, and once you have the condition, then you define this TC to be like this. You can see that this is T transport as well, and the algorithm now reduces to this when we consider the phi to be an indicator function of the power centers at x0 and of radius 10. So in that case, we generated this result. That is what for different U, well, we have this, for W we take, so it turns out to be this, and which shows the convergence. And we take how many? 1, 2, 3, 4. We take 4 different set of points at each one, and it turns out to give this result. And then when we define phi, just to be certain, what do you call convex proper continuous function, and that's one is not even convex in the classical sense, then we can see this one, we generated this kind of thing. However, in the process of generating this, we made use of admin search function of MATLAB, which of course, to some extent, make use of linear structure. But for the previous one, that is strictly for the case of the projection. This is, we give the explicit formula for the projection as well. This is very important, and you can see for the 4 different points, it may appear this way. For both UN and FN at the starting point, but at the end of the day, all of them, goes in phase with respect to the relative error. And also, this is how it started for the second one. It goes this way, but at the end, it's turned out to give a significant convergence. So this is actually what's happened. Yes, of course, for people that are interested in this kind of spaces, they can liaise with these study materials, and of course they will provide dense literature with respect to geodesic spaces, especially at zero spaces. This is a very, very important result, as it has been for a long time. People try to start investigating monotone variation inequality in case of KMUTT zero space, but it hasn't been in any literature yet. So we are happy to establish this kind of result, and we hope people can proceed to investigate further. Thank you for your attention. I expect questions and comments.
Any question or suggestion? If you have question, you can turn on your microphone and ask me.
Hello, Sani.
Yes, doctor.
Hello.
Yes, doctor, I can hear you. Can you please?
Hello.
Doctor, I can hear you. Can you hear me?
Yes, I can hear you now. Thank you for a nice presentation. This is a very nice result. I remember it has been in existence, like you said, and many people try to extend it to different problems, especially in the space, which so they have encountered a lot of troubles. But congratulations for. But my question is just a simple question or observation. Aren't you curious now to see whether this golden ratio techniques helps in improving the convergence, even though I know that it's not the target?
Yeah, I think it's interesting to investigate if really the golden ratio affects the convergence. The issue now is, the golden ratio has been used and it helps in getting rid of certain terms along the line of the proof. But we haven't tried other operators. For example, taking arbitrarily element coming from 0, 1. We haven't tried that yet because for now, the most important is just to have the study of up to for monotone type variational inequality. So as it is here, the golden ratio term is this 5, which is of course bigger than 1. When you take 1 over it turns out to be within 0 and 1. And I think it will be interesting if this kind of result can be built for arbitrary element in 0, 1, or if it can be taken to be a sequence. And that way, maybe if there is need of any condition that one may enforce on the parameters, then we can investigate the relationship between, the varying one and that of the fixed golden ratio and see how it is. I take note of this and it should be considered in the future work. Thank you.
Yeah, that's good. That's great. Impressive.
Hello, Dr. Sani.
Yes, Dr. Mahmoud.
That's a very good, interesting talk. I really appreciate the introduction towards the discussion behind how you try to relate this idea of golden ratio into your own setting of Hadamard space. So I wanted to briefly ask on this slide, since you are in this slide number 13. I wanted to understand how did you define this lambda k, and what is the effect of lambda k you come across, maybe from the convergence or from the experimentation? What's the effect of it, and then how do you define it?
Okay. For this algorithm to be well defined in the setting of part zero space, we only require that lambda k to be any element of 0, 1. Of course, once it comes from this interval, then the algorithm is well defined. But however, in the case of convergence, we may have to enforce additional condition. And this additional condition, you can see it here. Here, sorry, I'm trying to close this. Okay, can you see the convergence results, this one clearly? Yes. So you can see lambda k here is a sequence that converges to certain element, let's say alpha within this interval. Of course, I put it as a sequence because it can be a fixed. For example, take lambda k to just be alpha, any element within this interval 0 and 1. Then it turns out this one will also fall within 0 and 1. That is, it is well defined based on that algorithm. And then it will help us to get rid of certain terms in the proof, in the proof of the results based on this 1/L condition. And this is equivalent to the condition used by Milisky in his article 2020 of golden ratio 2020. It's a step size. I'm trying to get back to the golden ratio. Yes. So this is, his own is fixed. Our own is variant. So you can take this situation when our own become fixed. In that case, he also requires that this one has to be on the interval 0 to 2π/L. And that is the condition required for him. But remember, once we put that condition 2π/L, then you will see that yes, phi is also falling within the range, because phi need to satisfy this condition. Yes. So that is what's actually given. Well, I haven't, I haven't tried different selection of this phi in my algorithm. So what I did for this numerical that I show, I simply take the end point. For example,
the end point of the interval, right?
Yes. I take the end point and I consider it to be just 2π over L plus 1. That's what I did. Oh, I'm sorry, I did not mention it. Yeah.
It's okay. If I understand, you try to in your experimentation, for example, when implementing the algorithm, you basically try to define the alpha in terms of the L, which I believe resembles the Lipschitz constant, right? If I understand.
Yes, the L there is the Lipschitz constant, of course.
So for the experimentation, you need to explicitly get the value of the Lipschitz constant and then use it in defining the lambda.
Right? Yes, in some sense, yes. But remember, one thing that we need to take note here is that getting the Lipschitz constant is not really important, because if a map is 3 Lipschitz, that is to say, it's Lipschitz with constant 3, then it's also Lipschitz with constant 5, 6, 7, up to 100, 1,000, 1 million. Anyone you take is okay. So you see, ideally, people claim that, of course, one needs the knowledge of Lipschitz constant, but really, what is important is not exactly the Lipschitz constant. One can always estimate the upper bound of it, and any element would also help you in estimating the value. That's
Okay, so it's not problem dependent. So you can decide to take whatever value that you wish to represent the Lipschitz constant, regardless of the kind of problem you are dealing with. There is no restriction regarding that, right?
no, not regardless of the kind of problem. First, you need to have the map. You need to ensure that the map is Lipschitz. If it is Lipschitz, but do we really need to know exact Lipschitz constant? No. We can also estimate. For example, now I can take an example of a map that is non-expansive. By non-expansive means it's Lipschitz with Lipschitz equals to 1.
Yes.
So do I necessarily need to make use of 1? No. I can use any number bigger than or equals to
1. Okay, so I understand your point.
Yes, because once it is non-expansive, then it is Lipschitz for every L bigger or equals to 1. That is how it is.
Okay. Thank you very much for this talk.
Yeah. Please, more questions, please. More comments, suggestions?
Okay. No. Any question? Thank you for your nice present, Sunny.
Thank you, P-Head. You have to ask me a question.
No.
Okay, thank you. Thank you, Head.
Okay, next presenter, Adamu, are you here? Hello, Adamu.
Hello, Labit.
Okay.
Kokoma Labit. Okay, just a minute.
Okay.
Yeah, just in a minute.
Okay. If you're ready, you can start. You can share your screen and start. Okay, we have a plate. Maybe we start on 2:15. Okay.
Okay.
You have
30
minutes for present and question.
Okay. Good afternoon, all. My name is Adam Yusufino, and I'm going to present my individual seminar. The topic is application of equilibrium problem to generalize Nash equilibrium problem over a fuzzy set. Okay. So this is the content of the presentation. So actually, the work is at its early stage, so we don't have much. It's just going to be just 3 things. We're going to look at an overview of the motivation, and we just have some small introduction, and that's all. Maybe in the next 2 months, during my progress report, you will discuss more about the problem. Okay, so this is the overview. First of all, we look at the motivation for studying the Nash equilibrium problem over a fuzzy strategy set. Then in the second section, we'll give some introduction and some basic definitions. Then in the third section, we'll present the model. Then in the last section, we'll give some talk about the four solution method. For the motivation, now if you look at in every society, in every country, the development of country depends on the number of industries it has And those industries normally they operate in a kind of a Nash game. They compete with one another, especially if they have the same product. For example, in this case, suppose you have companies that are producing shoes. So since they are having the same product, normally they compete. Each company will be trying to maximize its production and profit. So in doing so, that has some positive effect on the society, on the government, and it has some negative effect. For example, if the companies, as they compete, they normally, if they are trying to improve their production, that will lead to the improvement in the economy. They employ many people, which will increase the employment rate in the countries. On the other hand, as they work, they normally harm the environment through the sewage and the emission they produce. So for the government, it has some concerns. On one hand, it wants the economy to be sustainable. On the other hand, it needs this waste to be minimized. The government does not want the environment to be degraded, but it wants its people to be employed, and it wants the economy to be boosted. So you see, government has objective, and the companies also has objective. So we are kind of having a viable game. That's what we normally have. On the top is the government, and on the lower level we have the companies which are competing in a generalized Nash game. So now here we give a definition of the generalized Nash game. So suppose there are I players, and each player contains control its decision variable, which will denote by UI, and we denote the vector formed by all those decision variable by this, where the vector UI represents the decision of player I, and UI minus Y is going to denote the decision of all players other than player I. So we denote the profit function for a player I by capital UI minus 1, and then the aim of each player will be to maximize his own profit. So he's going to maximize his own function. Sorry for this. This is a typo. So each player is trying to minimize his own profit function. So suppose we denote the solution of this problem by SUI minus SU star minus I. Then the analyzed Nash game is a problem of finding a vector UI such that a vector U star, which is denoted by this, such that UI star is in SUI minus 1 star for all I, and that none of the players can be able to improve his own profit by arbitrarily changing his own strategy. So here also define what is a fuzzy set. So a fuzzy set is a pair U and M, where U is a set and M is a function from U into 1, which we normally call the membership function. And the value of MX is called the grade of membership of X. So if U is 0, then X is not a member of U. If it is between 0 and X, is a member of if it is 1, then that point is a member of the complete member of the set. It is 1, and the degree of the membership, if it is between 0 and 1, then it is somehow in that time the degree of the membership of the point in X. And then we define an alpha cut set by this relation 3. So having this, then we now formulate our model. So suppose there are I farms in the region, and then the farms I profit function, if we denote it by UI, and it is production value by UI, small UI, and we denote the amount of sewage delivered by each factory by X, which is A of U. So in order to protect the environment, the sewage needs to be restricted. So the restriction of the sewage is going to be formulated by an alpha cut set, which is given by this. So then we can derive the profit and production value for the equilibrium model using this model 3. So this is the Nash equilibrium model for the companies. So if we let up to the objective function of the government, then our aim is to find a pair of solution U star alpha star such that f of U star alpha star reach an optimum value, where U star is the Nash equilibrium point for problem 3. So based on this, we are going to have the following bi-level model which is given by equation 4. So this is the model we are interested in studying. So we are trying to maximize f of U alpha subject to U and alpha in omega, where omega is given by U and alpha and 0 and U is the solution of the Nash problem given in 3. So what we intend to do is we are intending to formulate the lower level problem as an equilibrium problem, following the method given by Nasri and Mustafa in 2011, where they provide a link between an equilibrium problem and a generalized Nash games, whereby an equilibrium problem is the definition of an equilibrium problem is given as follows. So suppose you have a K is an empty set and F is a Bayer function, then we define the equilibrium problem as a problem of finding of X tilde in K such that F of X tilde, is bigger than equal to 0 for every point where in K. And we normally get the set of solution of equilibrium problem by EKF, and this is coined by actually in 1993. And as I said, this is just the work is just beginning. So I think this is all I am presenting for now. Thank you for your time. Is there any question?
Any answer ba zan yi tambaya wannan?
Any question? Okay, if no question, thank you for my presentation, Ramo.
Okay, thank you also.
Last presenter for today, Mr. Arif. If you're ready, you can share your screen and let's start.
Yes, I'm ready. Thank you. As the screen is visible. Hello. Can you see my screen?
Yeah.
Okay. Good afternoon, everyone. Thank you for giving me an opportunity to present my research. Thank you, KMUTT Fixed Point Lab, to organize such kind of series and give me an opportunity to present my research in this wonderful series. First of all, I would introduce shortly myself. I'm Muhammad Arif, working under the supervision of Professor Pomkomom and Associate Professor Dr. Ruben Sakothai. I am a PhD student at KMUTT and working as an international visiting research trainee at York University, Toronto, Canada. The topic for today's presentation is the proportional Caputo operator approach to the thermal transport of Jeffrey trihybrid nanofluids in a rotating frame with thermal radiation. So this is my presentation outline. In this, I will start from the introduction, and then I will move to the mathematical modeling and then I will show some solution of the problem. Then I will discuss methodology, and after that I will discuss some graphical results and its discussions. Then I will explain conclusion, which summarize my whole research, and at the end I will discuss some future directions. These are my research highlights. Being a researcher in the fluid dynamics, we deal with heat and mass transfer phenomena. So for the application of heat and mass transfer, we need to discuss the nanofluid, hybrid nanofluid, and tri-hybrid nanofluid, which are hot topics in this research area. Also, different shape of nanoparticles also affect these heat transfer performance. In order to discuss its heat transfer performance, we calculate rate of heat transfer. And these nanoparticles have useful applications in engineering and medical sciences. Then I will transform the classical solution into a classical model into fractionalized model. At the end, I will discuss some future direction. Introduction starts from background study that consists of some basic definition, brief statement on literature, review some problem statements, and then I will discuss objectives and application of fractional calculus, and also some of the applications of nanoparticles. Starting from the basic definition, which is fluid, anything which deform under the applied shear stress, that is called fluid. And in fluid dynamics, we have a Newton law of viscosity. This law states that shear stress is directly proportional to deformation rate. On the basis of this Newton law of viscosity, the fluid is mainly divided into two categories. Those fluids which obey Newton law of viscosity are called Newtonian fluids, and Newtonian fluids are, and the fluids which do not obey Newton law of viscosity, they are known as non-Newtonian fluids. And the example of non-Newtonian fluid are oil, honey, blood, etc. These are the examples. Different types of fluid flow. A steady flow. In this kind of fluid flow, the velocity of the fluid at any point is constant with respect to time. It, in simple words, that this kind of flow don't depend on time. An unsteady flow is the flow exists whenever the velocity of the fluid at any point changes with respect to time. And turbulent flow is the fluid flow, which is an extreme kind of unsteady flow. As we have considered the heat transfer in our analysis, so what is heat transfer? The exchange of heat transfer from one object to another object due to temperature differences. And this heat can be transferred in three different ways. The one is conduction, the second one is convection, and the third one is radiation. These phenomena, as you can see from the figure, conduction is the heat transfer rate through direct contact of particles. That is conduction. This kind of heat transfer is called conduction. And convection is the heat transfer because due to the transfer of particles from high concentrated or high temperature region to the lower temperature region. So this is convection. And the last one is radiation, the heat transfer through electromagnetic waves. Now I will define that what is conventional fluid. The fluid without nanoparticles, they are called conventional fluids. But comparatively, if you study the fluid and solid particles, so the thermal performance of solid particle is higher than the fluids. That's why scientists were trying to dissolve these solid particles in the fluid in order to enhance their performance. So many researchers were trying. The initial experiment was done by Maxwell, and he tried to dissolve some microsolid particle in the fluids. But these microfluid experiment was failed due to the sedimentation and clogging and blockage of the narrow channels. After this unsuccessful experiment in 1995, Choi at Oregon National Laboratory, he investigated that if a nanometer sized particle are added to a base fluid, so the resultant fluid will be a nanofluid, and this nanofluid have no such kind of sedimentation process, and this was a successful experiment. So actually, how to form the nanofluid? Nanoparticle are added in a base fluid, and there is it can be dispersed in a mechanical stirring or ultrasonication or dispersion, and the resultant fluid is known as nanofluid. After that, many researchers were trying to investigate this fluid and this idea in different fields of sciences. Some of the applications are here. Industrial cooling applications nanofluid play a vital role, a key role in this. Similarly, nuclear reactors, biomedical applications, smart fluidics, automotive applications, and agriculture application. In the current research, we discussed this application. We take engine oil as a base fluid and consider some nanoparticles to enhance the heat transfer rate. After the nanofluid, the researchers they took advantage from the nanofluids, and they still want to improve the heat transfer rate. So they suspend two different kinds of nanoparticles at the same time in a single base fluid, and that mixture is formed, and this mixture is known as hybrid nanofluid, which was more better than the nanofluid. And after the hybrid nanofluid, recently, the very recent study is trihybrid nanofluid, which is like the suspension of three different nanoparticles in a single base fluid, and this mixture is known as trihybrid nanofluid. A short history of the fractional derivative. 30th September 1960. L'Hopital wrote a letter to Leibniz that what will happen if we put this in fractional form, 1/2. This is the general form of the derivative or the nth derivative. So what will happen if we put this n is 1/2? So Leibniz responded that it's a paradox, and from one day, which will have some useful consequences will be drawn. And this letter was written by Leibniz to L'Hopital in 30th September 1695, almost 300 years ago. After that, the fractional derivative researchers were trying to work on this field, and many fractional operators and fractional definitions were developed by different researchers. Most famous are here listed. The first one is Riemann-Levy fractional derivative. After that, Caputo bring a new definition in the fractional calculus. After Caputo derivative, Caputo and Fabrizio developed a new fractional derivative a few years ago, and recently Atangana Balino fractional derivative. Atangana Balino developed a non-local and non-singular kernel. And recently, constant proportion Caputo operator, CPC operator, which is the hybrid fractional operator combined by combining the constant proportional and Caputo operator. So in my research, I have applied this operator on my model. So the main motivation of the present research are Jeffrey fluid in a rotating frame, and second one is fractional derivative, constant proportional Caputo fractional operator. In this kind of mathematical model, this is first time to apply this operator. And engine oil chosen as base fluid, and three different kinds of nanoparticles are dissolved in that engine oil base fluid. Furthermore, different shaped nanoparticles, which make this study more unique and more new work. This is my methodology. On the basis of this methodology, first we propose a problem on the basis of some assumptions. That problem gave us some mathematical modeling along with some initial and boundary conditions. And the system of equation with initial and boundary condition, we apply some non-dimensionalization process to make the system dimensionless. So after applying this process, we get dimensionless initial and boundary conditions. And then the dimensionless system of equation, we apply the classical model is fractionalized by taking the fractional operator, which is known as constant proportional Caputo operator. The transform boundary condition, and then by solving, we apply the Laplace transform technique, so which help us to convert the partial differential equations into ordinary differential equations. And as the problem in this research we consider as a very complex problem, so the Laplace inverse is not possible, so we solve it analytically using Streff's algorithm. And during the solution of the current problem, we calculated some limiting solution and validation of our result in the already published work. And then velocity and temperature fields are plotted in various graphs using MathCAD. And after that, we discuss some results and discussion, and finally we'll discuss conclusion. So this is the main problem. This is a geometry of the problem that we have a momentum boundary layer, thermal boundary layer. The base fluid is engine oil, and we suspend 3 different nanoparticles. I will explain it later. The condition at the plate is constant velocity. The plate is moving with constant velocity, and the temperature at the plate is wall temperature. And this temperature is rotating along z-axis. Okay, so on the basis of our assumptions, the momentum equation is presented in equation 1 and 2 in the form of primary and secondary velocity. U represents the primary velocity and V represents the secondary velocity. Rho is the density, and this THNF in the subscript shows the trihybrid nanofluid, where this ohm shows the rotating frame, and lambda 1 and lambda 2, this operator as a whole shows the Jeffrey fluid. And by combining these two equations, we get equation 3, which obtained from equation 1 and 2, and this is we can say that the complex velocity, which is obtained by the combining of these two primary and secondary velocity. And this F represent here the combination of primary and secondary velocity. U is the primary and iota V is the secondary velocity. Also, we consider the temperature differences. So the temperature equation with thermal radiation is expressed as in equation 4, and we apply some mathematical calculation, which is already mentioned in many papers, and so that's why for short time I just write the direct. After some calculation, we get equation 5 by linearizing this term Q, and we get equation 5. These are my initial and boundary conditions. Initially, the fluid were at rest, and the temperature was ambient. After some time, when t greater than 0, the plates start moving with constant velocity, and the temperature rises to the wall temperature. And far away from the temperature, the velocity 0, and the temperature becomes ambient. As we have considered engine oil, so engine oil is in the class of non-Newtonian fluid. That's why we consider, and Jeffrey fluid is also a non-Newtonian fluid, so we consider engine oil in this study as a base fluid. And we want to see the efficiency of 3 different nanoparticles: copper oxide, aluminum oxide, and titanium oxide in this engine oil by making the mixture of these 3 nanoparticles. The first one, copper, is we consider the spherical shape, aluminum is considered as platelet shape, and titanium is considered as in cylindrical shape. So the combination or the mixture of these nanoparticles in the engine oil, and we see the effect of these nanoparticles in the heat transfer rate. These are the steps for preparing the mixture of the nanoparticles. First, we consider nanoparticles, 3 different shapes, and the base fluid engine oil, and we combine all these nanoparticles in a single base fluid, and we get the trihybrid nanofluid. This is very important for the analysis, that evaluation of ternary hybrid nanofluid using mixture model. Mixture model was Sahu and Sarkar in 2019. They investigate this correlation for trihybrid nanofluid. So the density of trihybrid nanofluid is given here. This one you can see. So we have phi is the volume fraction of copper oxide, aluminum oxide, and titanium oxide. So in this case, this density is the combined density obtained from the volume fraction of copper oxide, aluminum oxide, and titanium oxide. Similarly, the specific heat and the thermal coefficient heat, all these so these are the evaluation of ternary hybrid nanofluid, which shows the impact of copper, aluminum, and titanium at the same time. One important factor, which is known as like a different shape, which is very important in heat transfer rate. So here I would like to discuss it. In the calculation, we discussed some from the expression given, which is mentioned in the calculation, that n is represented by 3 by psi, which shows the shape vector of the nanoparticles. And this shape vector depends on the value of n and psi. So further, this research explained that the 3 various kind of additives with different shape have been calculated. So first we consider the value of psi, n, and n1. So if we put these two values 1, the expression then obtained for the spherical shape. So that will be a spherical shape. Secondly, by considering this psi 0.612 and n 4.9, then the expression will be used for the cylindrical shape of the nanoparticles. And finally, this value, if we take 0.52 and n 5.7, the result will be obtained for the shape of nanoparticles. So these are the 3 different kinds of nanoparticles we considered in our analysis. Moreover, by obtaining this expression for viscosity and thermal conductivity for various shape additives of viscosity using the mixture model, we get these 3 correlations. The first 2 shows the nanoparticles which has spherical shape, and the spherical shape nanoparticle are copper oxide in this study. And the platelet cylindrical shape are the aluminum, and the platelet shape are the titanium oxide. Okay, so after that, the final system of equations can be, as I mentioned earlier, that can be dimensionalized by using Buckingham-Pi theorem, and we obtain the following dimensionless variable. So using these dimensionless variable enable us to dimensionless the system of equation as follows. So equation 8 shows the dimensionless form of momentum equation, and equation 9 shows the dimensionless form of energy equation. And these are the dimensionless initial and boundary conditions. During the dimensionalization, we get some parameters, some dimensionless parameters, which are given here. And as I discussed earlier, that we have considered constant proportion Caputo operator. So this is the mathematical representation, the final results. I put only the final results. If you want to see more detail, I provide all the details in the paper. So you can see from there, and there are a lot of references. So constant proportion Caputo operator is the operator which combine the constant proportion and Caputo operator as a hybrid fraction operator. So the Laplace of that, when you apply that constant proportion operator on the function of time, then the Laplace of that will give you equation 12. So now we have our system of equations. So apply that constant proportion Caputo operator on time, and then the generalized form is given in equation 13 and 14. Applying the Laplace transform on the energy equation, we get equation 15. This is the final solution of the energy equation after applying the Laplace transform. So we get this result. And similarly, by applying the Laplace transform on the momentum equation, we get this final results where this x2s, x3s, and x1s is presented here. These are the, so in order to make our system, solution of the system in more easy way, so we use some simplification, and we use here an equation on slide number 34. So, and from the whole research, we follow the steps. First, we dimensionalize the process, the dimensionalization process, then applying this CPC operator using the Laplace transform, and for the numerical solution, we use Stiff's algorithm. In our solution, we reduce our obtained solution to the already published result as a limiting case in order to verify and validate our results. So this section provides the limiting case by putting the rotation parameter. If we ignore this rotation and the alpha, which is the fraction operator, tends to 1, and the volume fraction also ignored, which is the trihybrid and improved 0. So by ignoring these three factors, our fractional trihybrid nanofluid model of Jeffrey fluid in a rotating frame will reduce to the Jeffrey fluid in the absence of rotation, which was done by Khan et al. 66. So this result verify our obtained solutions. So the comparison of our solution to the solution obtained by this is elucidated in figure 11. In the next slide, I will show the comparison of our present study and published study. So the solution are plotted using MathCAD software in order to highlight the impact of various and varied parameters on the fluid flow. So the first figure, figure 3, shows here the impact of two parameters. The one is alpha, which is fractional parameter. And the one is phi THNF trihybrid nanofluid, the volume fraction of trihybrid nanofluid. So if you look at first the fractional operator, by increasing this alpha, the velocity shows a variation. And we show that by applying this operator, we get more realistic results, and we get a generalized solution. So on the basis of, and by varying this fractional operator, we can get more general results. At the same time, the volume fraction can also affect the fluid flow. For 0.02, the volume fraction, keeping volume fraction 0.02, or you can say 2%, is equals to, the velocity is 2.6, right? And for 0.044%, if you increase this fraction, volume fraction, up to 4%, so the fluid velocity will decline, because the increase of this volume fraction can produce some resistance within the fluid, or can increase the viscosity of the fluid, which enable the velocity, or which slow down the fluid velocity, as shown in figure. Figure 4 shows the impact of fractional operator on temperature profile as well. And in figure 4b, the impact of volume fraction on the temperature. So increasing this or changing this operator, fractional operator, the temperature of the fluid also varies, as shown in figure. Here in this case, the volume fraction, initially the red line shows no nanoparticle in the fluid, which is the red line. So the temperature is very low, right? And by taking 1% of the volume fraction of the mixture, of that mixture of all the 3 nanoparticles, here this HNF shows the hybrid nanofluid, means that 1% of all the 3 nanoparticles dissolve in the engine oil, which gave us this temperature, and 2% of all will give us this green, and the 4% will give it this line. So which shows that increasing the volume fraction, the temperature will get rise, because once you increase the addition of these nanoparticles volume, concentration. So there will some collision within the fluid, and that collision produce some kinetic energy. As a result, the temperature gets rise. We have considered radiation term, radiation impact on the fluid. So radiation and velocity is shown here. When we take radiation, say 1, so the velocity 2.2. By increasing this radiation 12, the velocity of the fluid gets higher. So it shows that increasing the radiation, the velocity of the real velocity of the fluid will higher. Here, this real of f of zt shows that we have a complex velocity. So we are dealing with the real velocity. We are ignoring that imaginary velocity. That's why the real of f of z I have written. Radiation impact on the temperature of the fluid. Radiation can cause an increase in the temperature of the fluid as well. And you can see the impact in the figure. As we have considered unsteady fluid, so the flow depends on time. So by changing the time, by increasing the time, the fluid will rise up. The velocity of the fluid will rise up. So by taking T2, the velocity was initially 2.2. After some time, when the time T3, the velocity rises to 3. So it shows that with the passage of time, the velocity increases. Time relaxation parameter, lambda 1, on the impact of this parameter on the velocity shows that by increasing this parameter, the velocity of the fluid rises up. And it is due to the fact that after applying some press, so it will increase the fluid velocity in the form of retardation. And the time relaxation, one parameter is time relaxation and the other one lambda shows the time retardation. So time retardation, they are opposite, quite opposite. In this case, time retardation decrease the velocity and time relaxation will increase the velocity. The rotation parameter on the fluid velocity, by increasing r from 1 to 2, the velocity of the fluid gets lower. The rotation parameter slow down the velocity. Thermal Glacier number shows an increasing impact on the velocity of the fluid. By increasing this, the buoyancy forces increases. As a result, the velocity of the fluid increases, as shown in figure. For GR80, the velocity is 2, and for GR90, the velocity is more than 3. So this shows that this thermal buoyancy force can help us, can increase the velocity of the fluid. And this one is the comparison. That, for example, one may ask a question that why you use trihybrid nanofluid. So this is for that answer. The trihybrid nanofluid, the heat transfer enhancement using the trihybrid nanofluid is more as compared to the hybrid nanofluid and regular fluid. And this can be shown in this figure. The red one is trihybrid nanofluid, which shows the higher temperature. Hybrid nanofluid is a little slighter decrease. And from this figure, one can see that the addition of 3 different kinds of nanoparticle in single phase fluid can enhance the heat transfer rate more as compared to hybrid nanofluid and regular fluid. As I discussed during the limiting case before that, we present a limiting case. This limiting case can help us to validate our present result with the already published work. So our present result is the green line, and the already published work is represented by this dotted red line. So if we ignore some of our parameters in our analysis, so our solution will quietly identical to the solution obtained in this reference number 66, which shows that the validity of our result. Considering nanoparticles in our study, we must study the Nusselt number, and we must look at the Nusselt number. So that's why this is very important table for our heat transfer rate. So Nusselt number impact due to the volume fraction of the trihybrid nanofluid, radiation, time, and fraction operator. So when we increase the volume fraction from 0.02 to 0.04, the Nusselt number increases, and for radiation 10, the Nusselt number decreases. Similarly, for time, this Nusselt number increases, and for fraction operator from 0.5 to 0.8, this number also increases. Now, percentage enhancement in Nusselt number, like keeping all the parameters fixed, and just we need to vary the volume fraction of the nanoparticles, tri-hybrid nanoparticles. So we see that initially it was 0. It means that no nanoparticles. 0.01, 1% of the tri-hybrid nanoparticles. 0.02 means 2%. And when we put 4%, so we can see that the heat transfer enhances up to 18.728% in the engine oil by suspending the different types of nanoparticles with different shape. So this is our main target, that by suspending these nanoparticles can enhance the heat transfer rate of the engine oil. These are some concluding remarks. During the present investigation, we consider the classical model of Jeffrey fluid, which have been generalized by applying constant proportion Kaput operator, which highlight the memory effect in the system and which can give us more realistic results. And the comparative study have been conducted between tri-hybrid nanofluid, hybrid nanofluid, and regular engine oil. And from the comparison, it showed that tri-hybrid nanofluid is more effective as compared to the hybrid nanofluid and nanofluid. 3 different kinds of nanoparticles are dissolved. The one copper, the second one is aluminum, and the third one is titanium oxide. And the different shapes are spherical, cylindrical, and platelet shapes. From the comparison, it has been calculated that energy production in the case of tri-hybrid nanofluid is higher as compared to other fluid like hybrid nanofluid, more nanofluid, and classical fluid. So the comparison highlights that tri-hybrid nanofluid is more effective compared to nanofluid and regular fluid. The rate of heat transfer, which enhanced up to 18.728% by suspending the mixture of these 3 different kinds of nanoparticles in a single base fluid engine oil. The thermal performance is higher for tri-hybrid nanofluid in engine oil and improve the efficiency of the working fluid. So the Jeffrey fluid velocity gets higher for higher values of alpha, nRT, and lambda 1, and the Jeffrey fluid velocity declines when increase the values of phi, lambda, and r. The temperature increases with the increase in alpha, phi, and nr. These are some future directions as someone can extend this study by using cylindrical domain, by using vertical plate, by using rotating frame. Sorry, this was a mistake. Rotating frame is also already considered in this study. Moving cylinder and rotating disc, etc. One can consider different boundary conditions. For example, temperature, one can consider different boundary conditions and different base fluid and nanoparticles for different reasons. And one can consider different non-neutrino fluid models, and one can consider different fractional operators and compare their results, their outcomes. Also, discuss some nanoparticles for different engineering applications. This was the research activity. This paper last month published in scientific report. And that's all about for today. Thank you for listening. Thank you so much.
Any question? What's the question? Yes, Neil, you can ask him.
Okay. Thank you so much, Arif, for the clear presentation. Sure, you carry everybody along, but unfortunately, I get lost. When you were in the literature review around 96, you mentioned about the hybrid nanofluid. So my question now is, in the mathematical formulation of your work here, what we can see now in the comparison where you validate the result, you validate it with a model that consider a base fluid that is not rotational, right? Which in your case,
Yeah.
yeah. So what is relationship? What other relationship with the existing work in the literature with this your mathematical formulation? Are there
Like
any
for
that are related to this one? Apart from
the main reason by considering our present research to the already published work, which was I already published, compared with them, the only reason was I have considered Jeffrey fluid, right? And
yeah,
their model is also a Jeffrey fluid. I bring some modification in that Jeffrey fluid by changing the geometry, right? Their geometry was fixed. The geometry was not moving, but I consider the geometry in a rotating frame, right? So this was one modification in my new work. The second one is I consider the newly developed fractional operator, which is the combination of constant proportional Caputo operator and so they give us a hybrid fractional operator. So I applied that in the model, right? And the third modification is that I discussed the newly developed idea tri-hybrid nanofluid. So I study and I want to know that whether I am moving in the right direction or not. So for that, when you get your final result and you put the presence of that parameter which you already taken in the modeling, when you ignore the impact of that parameter and your result is reduced to that result which already published, right? So it means that your calculation is correct, your analysis is correct, because by ignoring your input and your result is already
yes, Dr. Arif, I understand what you are trying to say, and I agree with you. My concern was you. I'm just it's more like a suggestion. Next time you should be more clear about the relationship with the existing work. You know,
yeah,
like
the relation between the existence work and
very
my work is Jeffrey fluid model.
the can work that you said is very related in the sense that you said they did not only consider the rotational fluid, which should be at least shown in the among the literature, so that we can see what and what is clear the contribution is. That is just what I'm asking. And also another thing is on the issue of the tri-hybrid that you are talking about. You know, we are not expert here. I get confused. Naively, I was looking at I was looking at it at when you show the comparisons. Now, what does that mean if you have a higher heat transfer? Like for instance, naively, if I have an engine oil in my car, I will expect by the time I have higher heat transfer there, then it will be quickly hot, and that's right.
So yeah,
That's
actually engine oil is considered because everyone is familiar
okay.
with the engine oil.
Yes, I'm just asking naively how you can explain why would that comparison shows that the hybrid is better in that sense? Because for me, when you say you have more heat transfer, like in the case of now you give an example with a base oil, engine oil, when you have a too much heat transfer, then that is what we are trying to avoid, right?
Yeah.
You don't want to have
Yeah,
overheating.
let me explain you this.
Yeah.
As the engine oil is moving in the grinding parts of the engine, right? So the grinding parts, they produce some friction forces, and that friction forces produce more heat. So to reduce that heat and provide some lubricity, we use engine oil, right? This engine oil, the main reason is to produce lubricity and to enhance the heat, to catch the heat from the hot region of the engine. So initially, the researchers, we use the regular engine oil. After we put 1 nanoparticles, so the nanoparticles, the heat, they reduce the heat, like they reduce the heat, they make the system like the engine cool. But the requirement of our requirement was not fulfilled. So that's why then researchers, they try to incorporate two different nanoparticles in order to make the system cool and to take the heat from the grinding part of the machine. That's why we are trying to dissolve three different kinds of nanoparticles. So by adding these three nanoparticles at the same time, it can keep the engine cool, and the lifespan of the machinery will be greater. Like if you use a normal engine oil in your car, you have to change it after 10 to 15 days. But if you are using hybrid nanofluid, you can use it for a longer period of time, and it will keep your engine cool, and the lubricity will be for long. So
Yes,
these are the main motivations.
confusion, because in the comparison it shows that the one with the tri-hybrid has higher temperature.
Higher heat transfer rate. Higher heat transfer rate means that it will absorb more heat from the engine.
Okay.
So that will keep the engine cool. Like the heat
Yes.
will transfer from the hotter region of the engine through the engine oil.
Okay, that's good. That's good. Thank you then.
You're welcome.
A nice talk.
Thank you so much, Jamil.
Any question? Okay, there's no question. Thank you, all of you for present and listening. Okay, please turn on your camera.